Hello everyone, I'm Xiang Li. I'm really excited here. I'm working on SAD at CoreOS. This is Hongchao from Cloudera. He is a ZooKeeper committer. Today we are going to talk about TaskGraph, a project that we have been working on with some ex-Googlers recently. TaskGraph is a distributed machine learning framework written in Go. It is designed for running on modern infrastructure. During this presentation, we will talk about the design principles behind TaskGraph and give you a tour about TaskGraph at high level. Hopefully, we can convince you to write your first or maybe your next distributed machine learning application using TaskGraph. Before we go into TaskGraph, let me motivate you why there needs to be another distributed data processing framework for modern infrastructure. There are already a handful of big data frameworks, including MapReduce, Spark, MPI, and more. MapReduce, or Hadoop, is probably the most famous one by far. MapReduce provides a simple and powerful interface that enables parallelization and distribution of large-scale computation. MapReduce was designed back to 2004, 10 years ago. It was designed for running on the traditional cluster inside Google. A traditional cluster consists of co-located and connected physical servers. The distributed system running on the traditional cluster needs to manage the physical machine resources themselves. For example, MapReduce has a special master task that manages all its worker tasks. When MapReduce framework bootstraps, it first needs to launch the master task on one of the machines that it can manage. After the master task starts, it will take over the control of the MapReduce framework. It will start more mapper tasks to begin the actual MapReduce operation. While the mapper is computing, the master task needs to check the health and progress of each mapper task to detect any failure. MapReduce usually starts hundreds of mapper tasks for parallelization. Failure is very frequent if you have a large number of machines. In this example, machine 5 failed due to disk issues or maybe power failure. The master task needs to restart the previous mapper task on machine 4 to resume the MapReduce operation. As you can see, when running on top of a traditional cluster, MapReduce is not only a big data processing framework, but also a simple cluster management system. After 10 years of development, the cluster inside Google today is not just a collection of servers like 2004. Now, the cluster infrastructure abstracts CPU, memory, storage, and other computation resources away from the physical machines. Application now can view the cluster as a collection of resources. So application can focus on using the resources rather than manage the physical machines. For example, when running on top of a cluster management system, MapReduce can ask the system to start 3 same mapper jobs. The cluster will choose the best place for the mapper to start and restart it if the machine fails. In a word, MapReduce now can utilize the cluster management system to allocate physical machines and handle physical failures. So MapReduce itself can focus more on the big data side. This simplifies the design of MapReduce a lot. John Fries, an actual Googler, once said, "I was initially quite intimidated by interacting with an enormous data center. Later, the entire data center was shrunk down into a small box on my desk. It was just another machine, and the physical size didn't matter to me anymore." The Google infrastructure was considered as its secret weapon for a long time. Just 1 month ago, the hints and allusions are over. Google published a paper to review the details about its cluster management system, Borg. Borg brings several major benefits to us. First, abstraction. Borg has the details of resource management. The application can submit tasks with resource requirements to Borg, and Borg will handle the actual scheduling work. Borg also operates with very high reliability and availability. Even if part of the Borg physical machine dies, it can still operate without a problem. Moreover, Borg can run workloads across tens of thousands of machines. It gives the application the same opportunity to run at a very large scale. Borg also provides better utilization of the resources inside your cluster. It schedules the submitted job to the best place it can run. Multiple distributed applications can share the same underlying physical pool of machines as well as get good SLA guarantees. More importantly, Google, CoreOS, Red Hat, and other companies are working together on an open source version of Borg, Kubernetes. So we believe Kubernetes is becoming the modern infrastructure near us also at Google, and we should start to utilize its power to build the next generation of big data processing framework. So here comes TaskGraph. It is built on top of years of big data processing and cluster management experience inside and outside Google. TaskGraph focuses on providing data and computation topology, logical task management, and global synchronization for the applications running on top of it. Let's give it to Hongchao, and he will talk about TaskGraph and how it utilizes the power of modern infrastructure.
Cool. So as we just mentioned, the modern infrastructure provides us very powerful guarantees. And that's one of the reasons I'm excited about TaskGraph. It's built on top of Kubernetes, etcd, gRPC, and utilizes the power of modern infrastructure. What's more, it's a framework for writing big data applications. Our ultimate goal is that user can implement MapReduce, Spark, and new kinds of machine learning applications on top. Why do we build TaskGraph? Well, we shouldn't do the duplicate work. We want to make good use of what modern infrastructure provides us. Applications should be supported natively on top. However, in our experience, building big data applications still involves many common, low-level details of distributed systems. It's very hard for users to handle problems like fault tolerance and distributed coordination. As a result, we want to build a framework to handle those low-level problems for user, and that's TaskGraph. I'm going to cover 3 layers of problems handled by TaskGraph. First, topology. At the beginning of the job, there was a bunch of standalone tasks. User creates a topology and connects them. Task implementation usually requests data from its neighbors. What we figure out is that we usually request from a logical group, not specific task. Let me explain with one example. Here in this case, we have defined the neighbors of 0 to be 1, 2, 3, and we need to request the data from each of them. But somehow the job changes and add task 4 to be another neighbor of 0. Now the user has to do all the coordination work and figure out 4 is a neighbor of 0 as well. Instead of specific task, we should request from a group of tasks. In this case, we are requesting from a group, say mapper or worker. Before, task 0 need to figure out the details of neighbors for this job. Now the details of which task, how many tasks are totally hidden from the user. User only need to say, I want to request some data from some group, which will be translated to a group of tasks automatically by TaskGraph. All in all, task for logical label can vary by deployment scenarios, but topology logic shouldn't change. We should abstract a layer between the specific task and topology. User only need to care about the logic of data flow. TaskGraph hides the details of data flow. Second, for high availability, a logical task should be supported by multiple physical containers. Kubernetes restart any task if they fail, but the failure will still be noticed. We want to hide the failure completely. Ultimately, from the user's perspective, there's always only one logical task. Neither which container is the primary node nor how to deliver the messages correctly to the corresponding parts is outside user's concern. This layer of details should be handled transparently by the framework. Third, global views such as topology iterations needs to be synchronized cluster-wide. For example, at some point of time, the job needs to change the topology and do something different. In order to ensure the correctness of the job, it needs to be guaranteed that every task has jumped to the next topology. As a result, we introduce epoch as a boundary to help synchronize the global view. TaskGraph handles the synchronization details and provides a guarantee that during the same epoch, the global view is unchanged. So I just discussed the 3 features of TaskGraph. Now let's go into how TaskGraph simplifies the work of building BWMF application. BWMF is the algorithm behind many popular recommendation systems. For the first step, communication, tasks in BWMF need to transfer the data with each other. Let's see how topology helps us here. With topology, the task only need to say, I want to request the D# from all the workers. But without topology, user need to figure out the details of workers himself. For the first step, every task needs to notify the master with a status. Let's see how logical tasks help us here. What if some failure happened on the master? With logical task, the part that failed is transparently replaced by a standby. From user's view, it looks like nothing has happened. But without logical task, everyone will be aware of the failure, wait for the master restart, and try to do all the reroutings themselves. Finally, after an iteration is finished, the master will call an API increment epoch, and then the entire job will jump to the next iteration. We can see here the global view now has changed. They transfer the T# and update the D#. With TaskGraph, user only need to focus on implementing the logic for specific epoch. The synchronization details are handled transparently. Back to the beginning, the modern infrastructure has provided us very powerful guarantees. We should make good use of them instead of doing the duplicate work. However, building big data applications still involves many low-level details. In 3 ways of topology, logical task, and epoch, we have built TaskGraph to help users solve those lower-level common problems. It is our ultimate goal to build TaskGraph as an efficient, modern framework for writing big data applications. In the end, I want to say that we are still in early stage. Please help us shape TaskGraph by providing feedback. Thank you.
Thank you.